Welcome to Chapter 7, Sampling and Sampling Distributions. Introduction. In a typical statistical inference problem, you want to discover one or more characteristics of the given population. Generally difficult or even impossible to contact each member of the population. Solution. Identify a sample of the population and then obtain information from the members of the sample. Chapter objectives. Discuss the sampling schemes generally used in real sampling applications. See how the information from sampling of the population can be used to infer the properties of the entire population. Sampling terminology. A population is a set of all members about which the study intends to make inferences. An inference is a statement about a numerical characteristic of the population. A frame is a list of all members of the population. This potential sample members are called sampling units. A probability sample is a sample in which the sampling units are chosen from the population according to the random mechanism. Judgmental sample is a sample in which the sampling units are chosen according to the sampler's judgment. Methods of selecting random samples. Different types of sampling schemes have different properties. There is typically a trade-off between cost and accuracy. Some sampling schemes are cheaper and easier to administer, whereas others are more costly, providing more accurate information. Simple random sampling. The simplest type of sampling scheme is called a simple random sampling. A simple random sampling of size n is one where each possible sample of the size n has the same chance of being chosen. Simple random samplings are the easiest to understand, and their statistical properties are the most straightforward. More complex random samples are often used in real applications. There are several ways random samples can be chosen, all of which involve random numbers. Example approach, n equals 5 and n equals 2 for a total of 10 samples. Generate a single random number with a random function in Excel. Divide the interval from 0 to 1 into 10 equal subintervals of the length 1/10 and see which subintervals the random sample falls. Choose the sample that corresponds with the subinterval. Sample families to analysis annual incomes. Using Excel to illustrate how random numbers function, RAND can be used to generate simple random samples. Solution: consider a frame of 40 families with annual income shown in column B. Choose a simple random sample size of 10 from the frame. Generate a column of 10 numbers in column F using the RAND function. Sort the row according to the random numbers and choose the first 10 families and sort. Simple random samples are used infrequently in real application. There are several reasons for this. Because each sample unit has the same chance of being sampled, simple random sampling can result in samples that are spread over a large geographic region. This can be sampling of extremely expensive, especially if personnel interviews are used. Simple random sampling requires that all sample units be identified prior to sampling. Sometimes this is infeasible. Simple random sampling can result in underrepresentation or overrepresentation of a certain segment or population. Using stat tools to generate simple random samples. The method described in example 7 part 1 is simple but somewhat tedious, especially if you need to generate more than one random sample. Fortunately, a general method is available in stat tools. This procedure generates any number of a sample random samples of a specific sample size from a given data set. It can be found in the Data Utilities drop-down list on the Stat ribbon tools. Sample accounts receivable at Spring Mills. Objective: to illustrate Stat Tools' method of choosing simple random samples and to demonstrate how simple samples are distributed. Solution: dataset contains 280 accounts receivable for Springs Mills Company. There's a single variable, the amount of the bill owed. Generate 25 random samples for each size, 15 each for the small customers only. Calculate the average amount owed and each random sample and construct a histogram of these 25 averages. By generating a fairly large number of random samples from the population of the account receivable, you can begin to see what the sampling distribution of the sample mean looks like. The resulting histogram, which is approximately bell-shaped, approximates the sampling distribution of the sample mean. And as you can see, this is what it looks like. Systematic sampling. Systematic sample provides a convenient way to choose the sample. First, divide the population size by the sample size, creating blocks. Next, use a random mechanism to choose a number between 1 and the number in each block. And generally, one of the first K members is selected randomly, and then every K member after this is selected. The value of K is called the sampling interval, and it requires a ratio of n, where n is the population. And so if I select number 6, my first is 6, then 12, then 18, 24, and so on. Stratified sampling. Suppose various subpopulations within the total population can be identified. These subpopulations are called strata. Instead of taking a simple random sample from the entire population, it might make more sense to select a simple random sample from each stratum separately. This sampling method is called stratified sampling. The advantage of stratified sampling: separate estimates can be obtained within each stratum, which would not be obtained with a simple random sample from the entire population. The accuracy of the resulting population estimates can be increased by using the appropriate defined strata. Define the strata such as there less variability within the individual strata than the population whole. The key to stratified sampling effectively is selecting the appropriate strata. What is the appropriate depends on the company's objective and product. There are many ways to choose sample size for each stratum, but most popular methods it is used proportionally samples. With proportional sample sizes, the proportional of the stratum is the sample is the same as the proportion of the stratocyte of the population. The advantage of proportional sample sizes is that they are very easy to determine. The disadvantage is they ignore differences and variabilities among the strata. Clustered sampling. In clustered sampling, the population is separated into clusters such as cities or city blocks. Then a random sample of the clusters is selected. The primary advantage of cluster sampling is sampling conveniency and possibly lower cost. The downside is the inferences drawn from the cluster sample can be less accurate from the given sample size other than the sampling plans. The key to selecting a cluster sample is to define the sampling units as the cluster at the city blocks, for example. Then a simple random sample of clusters can be chosen. Once the cluster is selected, it is typical to sample all of the population members in a selected cluster. Multi-stage sampling schemes. The cluster sampling scheme is an example of a single-stage sampling scheme. Real applications are often more complex than this, resulting in a multi-stage sampling scheme. For example, in a Gallup's nationwide survey, a random sample of approximately 300 locations is chosen in the first stage of the sampling process. City blocks on the geographical area are then randomly sampled from the first stage location in the second stage of the process. This is followed by systematic sampling of the household from each second stage area. An introduction to estimation. The purpose of any random sample, simple or otherwise, is to estimate the properties of the population from data observed in the same sample. The mathematical procedure appropriate for performing this estimation depends on which properties of the population are interested in and which type of random sampling scheme is used. For both simple random samples and more complex sample schemes, the concepts are the same. Sources of estimation error. There are two basic sources of error that can occur when a sample random population: sampling error, non-sampling error. Sampling error is an inevitable result of the basing inference of the random sample rather than on the entire population. Non-sampling error is quite different and can occur for a variety of reasons. Non-response bias occurs when a portion of the sample fails to respond to the survey. Non-truthful responses are particularly a problem when there are sensitive questions in the questionnaire. Measurement error occurs when the response to the questions do not reflect what the investigator had in mind, when questions are poorly worded. Voluntary response bias occurs when the subset of the people who respond to the survey differs in some important respect of all potential respondents. The potential for non-sampling error is enormous. However, unlike sampling error, it cannot be measured with probability theory. It can be controlled only by using appropriate sampling procedures and design good survey instruments. Terms in sampling. A point estimate is a single numeric value best guess of the population parameter based on data in a random sample. The sampling error, estimation error, is the difference between the point estimate and the true value of the population being estimated. The sampling distribution of any point estimate is the distribution of the point estimates for all possible samples of the given size from the population. Key terms in sampling. A confidence interval is the interval around the point estimate calculated the sample data, and this is very likely to contain the true value of the population parameter. An unbiased estimate is a point estimate such that the mean of the sampling distribution is equal to the true value of the population parameter being estimated. The standard error of the estimate is the standard deviation of the sampling distribution of the estimate. It measures how much estimates vary from the sample. Sample distribution of the sample mean. The sample distribution of the sample mean, X bar, has the following parameters. It is an unbiased estimate of the population mean as indicated in the equation E times X bar equals U. The standard error of the sample mean is given in the equation SE, there's the formula, where sigma is the standard deviation of the population and n is the sample size. It is customary to approximate the standard error by substituting the samples. If we go out two standard errors on either side of the sample mean, you are approximately 95% confident of capturing the population mean. Estimating mean for accounting receivable. To illustrate the meaning of the standard error of the mean in the sample of accounts receivable, an internal auditor for a furniture retailer wants to estimate the average of all accounts receivable. First, he samples 100 of the accounts as shown. He then calculates the sample mean, the sample deviation, and the approximation of the standard error. Finite population correction. General sample size is small relative to population size. There are situations, however, when the sample size is greater than 5% of the population. In this case, the formula with the standard error of the mean should be modified with a finite population correction, the FPC factor. This standard error of the mean is multiplied by FPC in order to make the corrections. The central limit theorem. For any population distribution with the mean of U and standard deviation sigma, a sample distribution of the sample mean X bar is approximately normal when the mean U and the standard deviation sigma divided by the sample size of the approximation improves n as it increases. This is called the central theorem. The important part of this result is the normality of the sample distribution. When you sum or average n randomly selected from values from any distribution normally or otherwise the distribution from the sum of the average is approximately normal, provided that n is sufficiently large. This is the primary reason why the normal distribution is relevant in so many real applications. Average winnings from a Wheel of Fortune. To illustrate the central theorem by a simulated of winning of the game of chance. Solution: the population is set of all outcomes you obtain from a single spin on the wheel, that all dollars values must be between 0 and 1,000. Each spin results in one randomly sampled dollar value from this population. Each replication of the experiment simulates n spins the wheel and calculates that average, that is the winning from these spins. Histogram of the winnings is formed for any value of n, where n is the number of spins. As the number of spins increases, the histogram starts to take shape, and it's a bell shape. So with a single spin, 3, 6, 10 spins, we can see the formation of the histogram as we collect more data. Sample size selection. The problem of selecting the appropriate sample size in any sampling context is not an easy one, but it must be faced in the planning stages before any sampling is done. The sampling error tends to decrease as the sample size increases. So the desire to minimize sample size error occurs, you select larger samples. However, several other factors encourage us to select smaller samples, include cost, timely collection of the data, increased chance of non-sampling error, such as non-responses. Summary of key ideas for sampling random. To estimate a population mean with a single random sample, the sample mean is typically used for a best guess. This estimate is called point of estimate. The accuracy of the point of estimate is measured by the standard error. It is the standard deviation of the sampling distribution of the point estimate. A confidence interval with 95% confidence for the population mean extends to the approximately 2 standard error on either side of the sample. From essential theorem, limit theorem, the sample distribution of x bar approximately normal when the n is reasonably large. There is an approximately 95% chance that the particular x bar will within 2 standard deviation of the population mean. The sampling error can be reduced by increasing the sample size. End of chapter 7, sampling.